Okay, this is the topic 5 revision video for GCSE Astronomy, Solar System Observation. So we're going to look at 5.1 to 5.8 and you can pause it and have a read through those and I'll move on. So 5.1, understand how to use pinhole projection to observe the sun safely. Obviously the sun is very dangerous to look at directly. It would damage your eyes in no time at all, so you have to find other ways to observe the sun. There are filters that you can put on a telescope. Obviously they can be dangerous if there's one little pinhole in them and it's going to damage your eyes. So a safer method is the pinhole projection, which is simply a small hole in a piece of card, and then you would have a piece of paper behind that, and then what would happen is the sunlight would shine through the hole and then you would get an image of the sun on your paper. So it's a very, very simple method. That is all there is to it. The image that comes through is upside down. You might not notice that for the sun, but it's really, very, very simple method and safely project it. You can do it through a telescope or you can just do it with the plain light, which is a pretty cheap way to observe solar eclipse, and sometimes you can see some details on the sun as well. So pinhole projection, you can see in the top left here, observing the solar eclipse. So very, very simple and safe way to observe the sun. 5.2, understand the observed motion of the sun follows an annual path called the ecliptic. So if we are to observe the sun, if we're to look at the sun, then behind the sun, the patch of sky that would be in its background would be on this plane we call the ecliptic plane. Okay, so there's certain patches of the sky that the sun would appear to go through. Now the sun isn't going through it, obviously. It's us moving around the sun. So we get to see the sun at different angles, and its background is always a different patch of sky. Well, actually, there's only 12 patches of sky that it goes through, and those are the constellations of the zodiac. So this is the ecliptic plane, or the ecliptic line, and it's an imaginary line drawn from Earth to the sun and then beyond. All the planets are very close to being on the ecliptic line, but none of them are on perfectly. If we measure how far away you are in terms of angle, Mercury is the furthest, 7 degrees, and Mars is the closest, 1.8 degrees. But they're all pretty close. So you can think of the planets on a flat plane going around. It's not a coincidence that they're all in a loop going around on that ecliptic plane. It's physics, but beyond the realms of this course. The way that the solar system formed, of course, when it was starting to form, it was a violent place with lots more planetary objects going around, and it was only these that got left over, really. So it all settled down to being in a very similar plane. But it means that, yeah, if we look this way towards the sun, then we'll see possibly Mercury and Venus, and then if we look this way away from the sun, or the 360 degrees around, of course they're not always all lined up in this way, so you could have Saturn on the other side, so take it and place it on the left hand side of the sun, and then we would see it potentially close to Venus and Mercury. But Venus and Mercury are never going to get too far away from the sun. You're always going to have to look towards the sun, which we'll get to later when we talk about greatest elongation. But the others could be 180 degrees from the sun. Okay, so if the Earth didn't have an axis, then the ecliptic line would always be directly above the equator. But because it does spin on an axis, then the ecliptic line is not always above the equator. You can see here the ecliptic line does cross the equator, so there will be certain times of year when the sun will be directly above the equator, 21st of March and 21st of September. Here the ecliptic line is directly above the Tropic of Cancer on the 21st of June, and on the 21st of December the ecliptic line would be directly above the Tropic of Capricorn. So you get these diagrams, which people would think are rather complex, but I assure you they're not too bad. We could plot where the ecliptic line is. So if we go back here and we observe where it goes through, so let's take the date here, and then this was the patch of sky that the sun was in. So when the Earth is here, then that will be a certain date, same date every year, and this patch of sky is where we see the sun. So we can plot the date against that patch of sky, or we can observe how high the sun appears to go throughout the different dates. There's a very important point here, which is the 0 hours right ascensions, and that's the 21st of March. So on the 21st of March, the point in the sky where the sun appears to be, which is directly above the equator, is our first point of Aries. It's not in Aries anymore, it's in Pisces due to precession, we'll get to that. But the sun will then appear to go higher and higher and higher in the sky until the 21st of June. It's at plus 23.5 degrees, which of course is the tilt of the Earth, the axis of the Earth. And then the 21st of June, 21st of June to the 21st of September. So on the 21st of September, it's crossing the ecliptic line is crossing 0 declination again, and that's going to then head south. So on the 21st of December, it's minus 23.5 degrees. So that would be directly above the Tropic of Capricorn, and then back to the 21st of March. So we had to come up with a way of putting numbers onto this celestial sphere. The celestial sphere is the imaginary sphere that surrounds the Earth. Imagine, obviously there's stars that are much further away than this, but imagine before we knew the depths of space. So we would just put all the stars onto this celestial sphere. And we had to come up with a way of finding our way around the celestial sphere. We did it with the Earth, with latitude and longitude. So we've done it with the celestial sphere. As we go from the equator, we've gone 10, 20, 30, 40, 50, 60, 70, 80, 90, plus 90 and minus 90. That's known as declination. Now, for the going around the equator, so how are we going to count that round? Well, instead of going in degrees, they decided to go in hours and minutes. So it's 24 hours, so as we're halfway round, we're 12 hours round, and then another 12 hours to get back to the start. So it's 24 hours all around. But with latitude and longitude, there was two obvious places where to start. We were obviously going to start at the equator, and then we had to decide on one, it's not as obvious as you'd say, which was Greenwich. But for right ascension, the place chosen was, as I've mentioned, the point that the ecliptic will be found in the sky on the 21st of March. So that point in the sky, which was in Aries when it was named, is the point where we measure right ascension from. Okay, so first point of Libra, first point of Aries. You can pause it again and have a look through this. But the spring equinox is the first point of Aries, and that's where we measure right ascension from. So obviously 6 months later you'd find the sun on the other side, which is the autumnal equinox, first point of Libra. They're not where they should be because of precession. You can read that, pause it if you want to. But the reason they're called the first point of Libra and the first point of Aries is when they were named, Aries was down here, or the ecliptic was moved around, and then Libra, of course, over here. And now you can see it's not in the right place it should be. So that's precession, which is the wobbling of the orbit. Okay, so where would we find the sun in the sky? Well, if you imagine that we didn't have any tilt, or even just take it to the 21st of March, then at 12 noon the sun would be directly overhead. So 90 degrees, we'd call that as you're standing. The altitude would be 90 degrees. So if you went 1 degree away from the equator, then it's not going to be directly above you. You'd have to look at a slight angle. It'd be 89 degrees. So if you went 10 degrees away, the sun would be 80 degrees altitude in the sky. So if you went 55 degrees away, which is where we live, 55 degrees north, declination, then you'd be 55 degrees taken off 90, which leaves it at 35 degrees. So the sun would be expected, without any axis, to be at 35 degrees, which is about here. But we do have a tilt. So on the 21st of June, we're tilted towards the sun by 23.5 degrees. So you can add 23.5 degrees onto that. So 35 degrees plus 23.5 degrees is 58.5 degrees. So you'd find the sun around 60 degrees in the sky, pretty high. But then you've got to, on the 21st December, take 23.5 degrees off 35, which is 11.5 degrees. So the sun is, between 10 and 15 degrees in the sky. So it's not very high at all in the winter, depths of winter. Okay, so that's why we get such a variance. And as mentioned before, the sun rises in the east and sets in the west only on 2 days of the year, which is the 21st of March and 21st of September. In the summer, it rises further northeast and sets further northwest, and in the winter it rises southeast and sets southwest. Okay, so we can also look at the ecliptic line on this chart. Now this chart has cropped up on the exams before, and it plots the right ascension against declination and where you'd find the sun. And then you can put a third thing onto the graph, which is why people think it's complex, because you've kind of got two things on the y-axis. The sun is at 0 hours on 21st of March, and the sun is at 12 hours on 21st of September, which is why we can put the dates along. So the path of the path of the sun tends to go to the left, right to left, which again is something that people seem to be uncomfortable with. So you could get asked to place the sun. You'll only ever get asked to place the sun on one of 4 points: 21st of March, 21st of June, 21st December, or 21st of September. So you just put it at 0 or at the peak of the curve. Or you could be asked to show which direction the sun is going in. So if you've just put it at 0, then an arrow pointing that way. Or you could be asked to put onto this the zodiacal band. So the zodiacal band is just, you would just draw a line above it that follows it and a line below it. And that would cover the constellations where you'd find the planets. Okay, so as the sun goes around, as the Earth goes around the sun, looking past it, you would see 12 different constellations. Okay, so if you remember this ecliptic plane here, which means that actually you're never going to look up a different angle away from the sun and see a planet. You're always going to look close to the ecliptic plane. So if we know the path of the ecliptic plane, then you know that somewhere along the ecliptic plane you're going to find every planet. Okay, so this is what you'd put in the exam. Just dotted lines either side, or solid lines, and that's the zodiacal band. Okay, so that means that, yeah, sometimes you will get the planets looking very, very close to each other. That doesn't mean they're particularly close, just in our line of sight, they are close. Now, next thing is the retrograde motion of planets. So the term planet means wanderer. All the stars in the sky follow the same pattern every night. So as you're looking north, they'll just go anti-clockwise around the pole star, and over 23 hours and 56 minutes they would do a full 360-degree rotation around the pole star. If you look south, they'll do the same things the sun does and that the moon does. They'll rise in the east, they'll set in the west, they'll be at their highest point when they cross what we call the meridian, which is directly south. The planets don't do that. The planets wander around the sky, hence the name wanderer. And this is plotting over a few months, and you'll see that it seems to go back on itself and then go back the original way it was going. The reason that occurs is because of essentially one planet being lapped by another. So if we look at Mars here and the Earth, when the Earth is here, it looks at Mars, and it appears to be here in the background of stars. As we both carry on the orbit, Mars would appear to be there. The third one, Mars is here. But then the fourth one, Mars is now here. It's gone back on itself. It's because we're lapping Mars. So now we were looking in front of us to see Mars, but as we lap it, we're now looking behind us to see Mars. I wouldn't expect this diagram needing to be drawn. It's just the idea of what retrograde motion is. The planets seem to go back on themselves and then carry on going forward over a period of months. Okay, so next is looking at meteors, meteor showers. So here's some information. So there's two types of meteors, two types of comets, I should say, which are long period comets and short period comets. Long period comets come from far away. This is they have a period of over 200 years. They originate from the Oort cloud, and short period comets from the Kuiper belt. So this is the Kuiper belt, which is around where Pluto is. Lots of objects around there, and then as we go further out, everything that we've just looked at is in that little dot there, and then we go very, very far out and you reach the Oort cloud, which is the very edge of our solar system. The solar system is defined as everything that's orbiting the sun. Okay, so comets leave a trail. When they go around the sun, they will start to melt, and they'll leave little bits and bobs around, sitting there in space. When they come through the atmosphere, you'll see, when these little bits and bobs, I should say, come through the atmosphere, you'll see streaks in the sky. But you get these things called meteor showers. So a meteor shower is a period of time where you'll get lots of streaks, all seeming to originate from the same point of sky. So it's not a coincidence that we're just getting lots and lots of little, what we might refer to as shooting stars. It's little bits of debris coming through. It's actually leftover bits from that path of the comet. So we call them meteor showers because a meteor is something that we see coming through the atmosphere, like a shooting star. It does have a different name when it's in space, meteoroid, and a different name when it's hit the ground, meteorite. Bit picky with the language, that. Anything brighter than -3 on the apparent magnitude scale will be classed as a fireball, and these things can light up the sky as they come through. Okay, so I said they seem to originate from the same point of sky. That point of sky is known as the radiant, and that term radiant is something that it would be useful to know. Radiant is the point of sky where the meteors, all the meteors appear to be coming from. We can predict that, so we can know the meteor shower that's going to be at that time of year, and we can figure out where the radiant will be, and we can say exactly where you need to look. And actually, in that particular constellation, this is in the constellation Perseus, that meteor shower we call the Perseids. Okay, there's another example of the meteor shower. So if you did a long exposure photograph, you could find the exact point where they appear to be coming from, known as the radiant. Okay, so this is real photographs taken, and pretty obvious where the radiant is, somewhere around here. Perseid meteor shower. Okay, so why are we getting all these things? Well, here's a very famous comet, Halley's Comet. So it will take its path around the sun, goes very far away, and then comes back. When it's very far away, the sun isn't affecting it in terms of melting it too much, so it won't be dropping off debris, but as it gets closer it starts to melt. It has two tails, its dust tail and its ion tail, and it starts to drop little bits of debris, ice and dust. So there's this black line, half of it, this half by the sun, would just be a little path of dust and ice. And as you can see, this blue line is the orbit of the Earth. So as the Earth passes through this trail, then those bits and bobs will come through the Earth's atmosphere, and we'll see them as meteor showers. You can get hundreds per hour coming through, which you could notice. Some meteor showers are very strong, some meteor showers are very weak. You don't see many at all. Okay, so this is meant to show more like the debris. So this is the Earth going through that, and then all this stuff comes through. Obviously, you know, it wouldn't last forever, but like year after year after year, we do get different bits coming through. But then eventually the comet's going to come past again on the same path, pretty much. So it will give us some replenishment of all the stuff that's going to come through as meteor showers. Okay, so this is another example of that with Comet Swift-Tuttle, and you can see the path of the comet with all the debris it's left, and you can see that the Earth, we can predict exactly when the Earth will pass through it, if it is on the same plane. So on August 13th we would expect very strong meteor showers from Comet Swift-Tuttle. So August 13th, which is around here, and you can see, we can predict it, and we can see how many we're going to get. And the big ones are the Quadrantids, and we've got the Perseids, and down here the Geminids, which are really strong, so you can sit out and see lots of meteors. Okay, so we'll finish with just these terms. So I mentioned Mercury and Venus at the start. Mercury and Venus will never appear far away from the Sun. Venus or Mercury, they'll either be here, or here, or here, or here. We're never going to be looking directly far away from the sun to see them. So if it's here, then it would seem to line up with the sun. If it's behind the sun, it would seem to line up with the sun. This is the point of greatest elongation. It's not at 9 o'clock and 3 o'clock. It's more like 4 o'clock and 10 o'clock where you get the point of greatest elongation defined there. Okay, conjunction. Conjunction is when planets appear to be very close to the sun. And here's some planets in conjunction here. And they seem to line up with the sun. But in opposition, that's when you'd look at the sun and then 180 degrees away from the sun, you'd see Saturn. You'd see the planet, sorry. So, with conjunction, you would have Earth, planet, sun, or Earth, sun, planet. But for opposition, you can see we've got the Earth, which is a complete opposite in between the planet and the sun. So they're 180 degrees out there. So it refers to the sun. If the planet can be in conjunction with the sun, if we're looking at both at a very similar time, or it can be in opposition to the sun when it's on the opposite side to the sun. Okay, and of course Mercury and Venus can never be in opposition. They just have two conjunctions. Transit is when a planet appears to go in front of the sun. Only Mercury and Venus have transits, you know, this is an example of just a smaller body passing in front of a larger body. There's another image of a transit there. Occultation is when a planet appears to go behind the sun. And here's an example of the kind of diagram that you get in the exam. So if you wanted to, if they gave you something like Venus and they asked you to place it when it would be at greatest elongation, it's the point when it would appear further. So you draw a line and you've just got to hit the edge of the circle. So I'd say about what is it, did I say 10 o'clock? It's about 4 o'clock or 8 o'clock. I think I said 10 before. So there are 2 points of greatest elongation. I said it will never have an opposition. Venus will never get behind it. So it will be in conjunction, and then 180 degrees later be in conjunction again. Inferior conjunction is when it's closest, and when you have a superior or a larger distance, it's superior conjunction. This it could be Saturn. So Saturn can have opposition, or it can have conjunction as well. The distance can be measured. So the distance from the Earth to the Sun is 1 AU. So let's say Venus was about 0.7 AU from the Sun. Then you can see if that's 0.7 and this is 1 AU, then this is 0.3 AU. So Venus actually gets very close to Earth. But there are times when Venus is 1 AU plus the 0.3. So 1.3 AU. So it can be 0.3 AU or it can be 1.3 AU away from the Earth. So it's always a difference of 1 AU. It's the same. But here you can see Saturn. Let's say Saturn was 5 AU. So here the Earth is 1 AU, and if Saturn was 5 AU, then that would be 4 AU, wouldn't it? But here, as Saturn is on this side, then we've got 1 AU plus another AU plus the 5. So that would be 7. So it would be 5 to 7. Whereas here we've got 1.3 to 0.3. So for the inferior planets there's a difference of 1 AU. For the superior planets, the further out planets, a difference of 2 AU. Okay, and that's all the terms. Hope that was helpful. That is the whole of topic 5 done. So try the questions and let me know if you have any questions. Thank you very much.